Hello, my name is Calvin Hawkins. I'm a second-year PhD student at the University of Florida. Today I'm presenting some results on applying differential privacy to formation control. So this work's a collaboration with my PhD advisor, Dr. Matthew Hale. So in multi-agent systems, the overarching idea is to have agents to communicate to achieve some common task. This work's concerned with how agents can collaborate to achieve a common goal while protecting their sensitive information. So for example, in autonomous driving, we may share our path home to help facilitate traffic management. However, doing that can reveal our location over time. So the question then arises, how can we get the benefits of collaboration but keep things private? And we can't anticipate all of the analysis that will be done with our trajectories that we share. So we need some sort of formal protection that guarantees that sensitive information is protected while still allowing data to be useful. So this leads us to the notion of privacy we use in this work. So in this work, we enforce privacy using differential privacy. Differential privacy is a statistical notion of privacy that originated in the computer science literature, and it's recently been extended to dynamic systems. So to illustrate the goals of differential privacy, we have an example here. We have two databases that differ in one entry. Here, the blue and green entry are different, and everything else in the database is the same. And a differentially private algorithm states that these two databases should produce outputs that are approximately indistinguishable, such that an adversary would not be able to reliably distinguish between these two outputs. And differential privacy is appealing for multi-agent systems because it's immune to post-processing, such that if I give you a private piece of data X, you can perform any operations or f of X on this data and privacy is preserved. And it's also robust to side information, where if you have outside information about me that I don't want you to have, the privacy guarantees aren't weakened by much. Differential privacy is used by several large companies such as Apple, Google, and Uber, and also differential privacy is being used in the 2020 census. So the odds are most of you listening to this presentation have used differential privacy in your day-to-day life. And using differential privacy for multi-agent systems allows agents to share trajectory data with other agents in a network while protecting their data from other agents and eavesdroppers. So now that we have an idea of what differential privacy is, I want to give a formal definition of it. So the goal of differential privacy is to make similar pieces of data appear approximately indistinguishable. And these terms are in quotations here to highlight that they're technical terms. And in differential privacy, we use an adjacency relationship to define when data is similar. So for agent I, two of their trajectories are adjacent if they are similar. And if this black circle represents agent I's trajectory and trajectory space, all of the trajectories within distance BI will be adjacent. So to define differential privacy, agent I picks two privacy parameters, epsilon and delta, which are both positive constants. And now we say that a randomized mechanism M is epsilon delta differentially private if it satisfies the bound shown here. And here epsilon can be thought of as the leakage of private information, and delta can be interpreted as the probability that differential privacy fails. And usually we consider epsilon less than 1, but the smaller the better. And delta should be as small as possible, typically using values 0.05 or less. So now that we have this privacy tool at our disposal, the question is, how can we use this in multi-agent coordination? We want to apply this notion of privacy to control problems that are already being used. And one common problem in multi-agent systems is formation control. So now I want to give some background on the formation control formulation we're considering. So consider we have a network of n agents, and at each time k, agent I has state xi of k. And if we're interested in robotics, these states will be a position and velocity, but depending on the application, these states could also be virtual states. And we consider networks where the communication topology can be modeled by a weighted and undirected graph. And we say if two agents I and j communicate, they want to maintain a relative distance of delta ij. And when privacy isn't being implemented, this can be achieved with the formation control protocol shown here. And in this controller, Ni is agent I's neighborhood set, or the set of all agents that agent I communicates with. So agent I updates its state with data from its neighborhood. And here we have a simulation of this protocol, and we can see that the agents are getting to their desired inter-agent distances, but we can see that this protocol is well suited for what we want to do. So at this point, we formally define differential privacy and the formation control protocol we're interested in. So now I want to formally define the problem we're going to solve. So the problem of interest is twofold. So first, we're going to implement the formation control protocol in a differentially private manner. So each agent keeps its trajectory differentially private. Um, And when we implement privacy, there's going to be a loss of performance in the controller. So the second part of the problem is to quantify the trade-offs between network performance, the level of privacy present in the system, and the underlying communication topology. So for example, these two graphs have different topologies, and that's reflected in their different values of algebraic connectivity, or lambda 2. And in multi-agent systems, lambda 2 is often useful to us. And in this work, we'll see that it encapsulates how the topology affects the private formation control. So given this problem statement, I now want to highlight what happens when we implement privacy and how it affects the formation control protocol. So as I previously mentioned, to achieve this formation, agent I needs to communicate its state xi to its neighborhood at every time k, but instead of sending its true state to its neighborhood, agent I is going to send a differentially private version of its state, which we call x tilde. And we achieve differential privacy using the Gaussian mechanism, which really means pointwise in time, agent I adds Gaussian noise V sub I to its state before sharing it. And this Gaussian noise is zero mean IID with standard deviation sigma I. And for each agent, the Gaussian mechanism is epsilon delta differentially private if the standard deviation of the noise is lower bounded by kappa bi. And here kappa is just a function of epsilon and delta, and k delta is the Q inverse function of delta. And to reiterate, b sub I defines the adjacency for agent I. So overall, this is saying if you give me an epsilon and delta, using this function, I can easily compute the required noise to achieve epsilon delta differential privacy. And to achieve privacy at the network level, each agent will use this mechanism. So to reiterate, agent I is going to add noise to its state to get its private state, and then it's going to send this private state to all the agents in its neighborhood set, and each agent is going to perform this. So when each agent implements privacy using the Gaussian mechanism, the formation protocol changes a little bit. So here the V sub j is privacy noise added by agent j. And as a consequence of implementing privacy, we incorporate a stochastic component into our controller, and we're no longer perfectly achieving the formation. And this is illustrated in the simulation here. The thicker lines represent each agent's trajectory when they're not using privacy, and the dashed lines are the trajectories when differential privacy is present. And of course, the dashed lines don't perfectly follow the solid lines, so incorporating privacy noise means we're no longer doing things perfectly, but we can clearly make out a formation here. And in light of the fact that the agents are keeping secrets from each other, they're actually doing rather well. So now this is just one simulation, so the question becomes how well are they doing, and how typical is this for other networks and other formations? So to quantify this, we define agent I's error as the difference between its state at time k and beta, where beta is the state that the non-private protocol will converge to with initial condition xk. So overall, E sub I is where you are compared to where you want to be. And at the network level, we define the steady state error as the lim sup of the mean square error present in the system. So essentially, we're analyzing the long run worst case error by taking the lim sup here. So now that I illustrated what happens when each agent implements differential privacy and how we're going to quantify the performance of the network, I want to state our main result. So with theorem one, we can obtain bounds on the steady state error of the network. And for a network of n agents running the formation control protocol shown here over a connected, undirected, weighted graph G, this controller is differentially private and has steady state error upper bounded by this expression. And this expression contains gamma, which is basically our step size, the size of the network n, the maximum variance of privacy noise, as well as the algebraic connectivity of the underlying graph G. So this means we're accounting for agents dynamics, the network size itself, privacy, and topology, all wrapped into this one nice scalar bound. So overall, this lets us quantify the trade-offs between performance, privacy in the system, and the underlying communication topology. So it directly solves the problem we're interested in solving. So to give you an idea of how this result was obtained, I modeled the formation control protocol as a Markov chain and proved that this Markov chain meets Kolmogorov's criterion, which allows us to obtain closed form bounds on the Kameni constant, and thus giving us this nice result in terms of the underlying communication topology. And to illustrate this result and the loss of performance due to privacy, I want to consider two examples. So for both examples, we fixed delta I equal to 0.05. And we also fixed the communication topology to be the star graph over 5 agents. And just to reiterate, a smaller epsilon implies a stronger level of privacy. And in case 1, we let each agent have epsilon equal to 0.8. In case 2, epsilon's equal to 0.1. So case 2 is much more private than case 1. So on the left, we can see even under pretty good privacy, there's a clear formation being assembled. And on the right, privacy is quite a bit stronger and we see a noticeable loss in performance. So usually this relationship between privacy and the required performance is a function of the application itself. And the results we obtained in this work allow us to balance the relationship between privacy and the required performance. So for example, suppose that we're tasked with designing a private formation control network that has to meet performance requirements, or in other words, the steady state error of the network can't exceed some specified ER. And Theorem 2 says that given this requirement, it will be impossible to design a network if the level of the privacy in the system follows this bound. And here we have an upper bound on epsilon. This can be interpreted as a maximum strength of privacy that is allowed in the network before the network will no longer satisfy the specified performance requirement. So overall, this is saying given a level of error and given a graph, this implies hard limits on how much privacy agents can have. So now this is all done under the assumption that we are given a graph, but in some cases we can exert some control on the topology itself and actually design it. Then as network designers, the question becomes what happens when we're not given a graph, and what graph would be best for us. So this has led us to consider network design problems of this nature. And specifically for future work, we're interested in optimal privacy and network co-design. So if we want to design an optimal network, we want to consider things like that the agents want to be as private as possible, but the network designer wants the network to have the best performance possible. And these goals directly compete with each other, but the trade-offs we quantified in this work allow us to balance these goals in a constraint of an optimization problem. And we also want to implement constraints on how many agents can communicate or how many edges we can afford to have in our network. So our goal is to design all of this into an optimization problem, and that will basically give you a result that says this is your optimal network communication topology and these are your optimal privacy parameters. And at this point, we formulated all of these goals into an optimization problem and proved that it's quasi-convex, meaning it's quasi-convex over the Cartesian product of the space of graph Laplacians and the space of privacy parameters. However, this problem is numerically hard, and we're currently working on obtaining some nice numerical results. But once that's done, we plan to open source this privacy network co-design code on GitHub. So that brings us to the end of this presentation. I'm happy to answer any questions you have throughout the sessions offered by the conference, or you feel free to email me at kelvin.hawkins@ufl.edu. And thank you everyone for coming.